Hello and welcome back to a new session. In this session, we are going to talk about the MSP430 microcontroller, continuing from our previous lecture. This is part of the online course on Introduction to Embedded System Design, and as usual, I am your instructor Dhananjay Gadre at Netaji Subhas University of Technology. Now, in the last lecture on MSP 430, we looked at the MSP 430 series map of the memory map, and specifically the G2553 microcontroller. We were looking at that here. Let us continue further. The flash memory, which in this case is 16 kilobytes of flash memory, is partitioned into segments. A segment is the smallest amount of memory that this microcontroller can erase, and the flash memory is partitioned in two parts as we discussed. One is the memory where you store the code, and the other is what is called as the information memory. The differences between the two segments here, the code segment and the information segment, is the size of the segment. The information segment is 64 byte segments, and the main memory is where you store the code is 512 bytes. In our case, the amount of memory that is available, you have in 2553 we have 16 kilobytes of memory. We have already discussed what all we can do with this, and I will repeat here that the flash memory can be used to store code as well as constants, and you can modify some of these constants also. The interrupt vectors are stored in the flash memory part of the code memory, in the very upper, the uppermost part of the flash memory here. This is the where you are storing the interrupts and the various interrupt vectors as well as the reset vector. We have seen that the reset vector is at address, let me write it down here, is at address F, 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 E and F, 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 F. You see it takes 2 bytes because the addresses are 16 bits, that is why you have to store these two locations, you have to use these two locations. Here is the table which describes all the interrupt vectors. G2553 supports 32 interrupts, and each of the interrupt requires an interrupt subroutine. Interrupt subroutine is going to be a program in the flash memory, and in this vector table you store the address of that location in the flash memory, and so each address is 16 bits, and so for 32 interrupts it requires 64 memory locations, and this is the description of that. As you can see, at the top of the location is the reset vector, and you have other interrupts associated with various peripherals of G2553. We will go in these details when we are using these peripherals. So, I am not going to go through each one of them, but as you can see from this table, it has interrupts for timers as well as comparators, a watchdog timer, the universal serial communication interfaces and the ADCs, and as well as ports. Now, the information memory of the flash memory is in the case of G2553, you have 256 bytes here, and it is starting from this address to this address. This is 256 bytes, and the information, these 256 bytes are split in 4 segments of 64 bytes each, as I mentioned earlier, and these are used to store various information. You can store constants, as well as the first segment is used to store factory calibration data for the digital controlled oscillator, the oscillator that uses the RC oscillators. You want them to be accurate, so each one of them is calibrated so that they provide your 16 megahertz or 8 megahertz clock frequency, and so that information is stored there. and this segment called segment A of the information memory is protected at reset. You cannot, after reset, when you are running the program, you cannot overwrite this information, because this is very critical information. The next part of the memory is what we call as the bootstrap loader. Now, I mentioned in the past that MSP430 microcontroller can be programmed in several ways. One of them is to use the SPI by wire protocol. The other is through the JTAG, 4 JTAG pins that we have on a microcontroller like MSP430, and the third method is through the bootloader, which is an in application programming method of uploading a code, and in MSP430 jargon this is called bootstrap loader, and that bootstrap loader is located at this address as you see here. This is the location, and in the case of MSP430 microcontrollers, you do not have to write that program. Each and every MSP430 microcontroller, especially the G series, they come with a pre-programmed bootstrap loader. All you have to do is, in your microcontroller system, provide an ecosystem which is compatible with invoking the bootstrap loader mechanism, and then you can upload any program from your desktop computer into the memory of the microcontroller, and later in this section we will discuss about that. But to mention here that about 1 kilobyte of flash memory is available and pre-programmed with a bootloader provided by Texas Instruments. The RAM is used for storing variables as well as stack, and you have about 512 bytes of SRAM available on the G255 series. Here is the address. This is the starting address 0200, and the upper limit of that address depends on exact chip number. In this case it is 512 bytes. So, from 0200 it will go up to 512 locations. Apart from the flash, the information flash and the RAM, you also have memory for use by the peripheral registers of the CPU, and you can see them here. And there are 3 types of registers. Some of the registers require 16-bit access, so they are available here, word access. Some of the peripherals require 8-bit storage, and so those registers are accessible through this. And then there are special function registers, which we will come to shortly. This is the various 16-bit word storage peripheral registers. As you can see, they deal with ADCs, they deal with timer 1 and timer 0, as well as flash memory. You can control access to the flash memory by writing into these registers, and you can also write to control the watchdog timer at this location. Then you have the peripheral modules for 8-bit peripherals, which is here, and by reading and writing 8-bit data into this information, you can control such peripherals. And here is a list. As you can see, there are much more than what you saw in the word accessible peripherals. This is the USCI, that is Universal Serial Communication Interface. The second module, you have some ADC devices, you have the comparator. The clock system can be controlled various low power modes by writing into this, and the ports P3 and P2 can be accessed, and similarly port 1 and other special function registers related to the interrupt control are accessible through these byte access special function registers. Well, I meant byte accessed peripheral registers. Then we have special function registers. These deal with here, these deal with various enabling of interrupts and allowing interrupts to function and flag registers related to them. The storage is 16 locations, 16 bytes. Now, we have reached a stage where we are ready to talk about the CPU in MSP430. This CPU is MSP430 is a RISC architecture, and as recommended by the RISC specifications which were brought forward in early 80s, RISC wanted all the CPUs to have large number of registers, so that local variables could be stored within the CPU rather than having to go in the external memory such as the RAM for fetching them, which slows down the execution. And in keeping with that recommendation, MSP430 has 16 general purpose registers. They are labeled from R0 here to R15. Each of these registers can store 16 bit of data. These registers feed a 16 bit ALU, as you see here. The ALU can perform various mathematical and logical operations like add, subtract and or operations, and the result of these operations can be observed through these flags, but these flags are accessible through one of these general purpose registers that we will see. So, we have in all 16 registers. Let us see the function of these registers. There are 4 special function registers, which means out of these 16, 4 are taken off because they have a dedicated function. One of the registers is a program counter, which means the content of this register will tell you which memory location in flash the microcontroller CPU is fetching the current instruction from. The second register is for stack pointer, which tells you that where is the stack located in the RAM. It is your responsibility to ensure that the stack pointer is pointing in the right memory of the RAM. And the third is a status register, which indicates the various flags that we just saw, whether the result of a particular CPU operation of add, whether the result is 0 or whether there is an overflow. All those flags will be available in this status register. And there is an interesting concept called constant generator. In many programs you require certain constants, and this constant generator offers you that flexibility without having to store them in your program. And then apart from that, you are left with 12 general purpose registers which the CPU utilizes. Now, since we are not going to program MSP430 in our course in assembly language program, we do not really worry about how these general purpose registers are going to be used. It is dependent on the C compiler or whichever compiler that we use to optimally use these registers, but to know that they exist is a great consolation that our program is going to be compiled efficiently. So, let us see which special registers we have. We have a program counter, and since the program counter deals with reading the next instruction, the instructions are all 16 bit wide, whereas our memory is arranged in terms of bytes, and therefore, the least significant bit here is set to 0, because we want to store all our instructions at even byte addresses, even addresses. So, our first instruction, if it is at 0, the next will be at 2, and then next will be at 4, and this can be ensured by ensuring the least significant bit is set to 0, and therefore, we have out of a potential 64 kilobyte memory space, we can actually store how many instructions? We can store half of them, 32,768 total instructions you can store. Of course, the actual number of instructions that you store will depend on the available memory, the flash memory that you have, but this kind of limits the maximum number of instructions that you can have. Instructions themselves could be one word, which means 2 bytes, or 2 words or 3 words, that is the depends on the exact instruction. Then the second register we have is a stack pointer. A stack pointer is a special register which points to the stack, and stack is that memory area where you are going to store your return address when you call a subroutine, or where the CPU stores the return address in case an interrupt subroutine gets called. So, this is the location, this is the RAM location in which you store your return address. Again, just like the program counter, the least significant bit is set to 0, so that it is able to write 16-bit numbers which refer to the address of your program, the return address, and therefore, this bit is 0, the rest of the bits are available to you, and of course, it is your responsibility to initialize the stack pointer appropriately. The third register is a status register, and the status register consists of various flags, and we will see the details of it. It also has access to the interrupt mask, so that you can enable disable interrupts, and it has some special flags which allow you to turn the CPU off or turn the oscillator off and so on, and we will see these operations subsequently in our exercises. We have a overflow flag which is set to 1 when the result is an overflow as a result of mathematical operations when you are dealing with signed bit numbers. We have these two system clock generator bits where you can turn on and turn off the main clock or the other clocks. You have oscillator off and so on, and here is the general purpose interrupt enable, and then these are the 3 flags apart from the overflow flag, which is the negative flag, which means when the result, the most significant bit of your number that you are looking at, if it is 1, this is the negative flag. You have the 0 flag when you do any mathematical operation or logical operations, it results in a 0 in all the bits, and a carry flag when there is a carry from the most significant bit into the outside that. So, these are the flags that are available. The constant generator register is able to provide 6 commonly used values using R2 and R3, and no special instruction is required to access those constant values, and we will look at a program so that we illustrate this concept. The rest of the general purpose registers can store 16-bit values, and you have 12 registers to do that, as you see here, from R4 to R15, and there is no dedicated function associated with these registers. These will depend on, if you are going to program in assembly language, then it is your responsibility to use them judiciously. If you are going to use a high level language compiler, then it is compiler's responsibility to use this register as it may deem fit. Now, since we are not going to program MSP430 in assembly language programming, but we still want to have a feel of the kind of instructions that are available. As I mentioned, MSP430 is a RISC architecture, which means the number of instructions expected is less compared to a corresponding CISC architecture. It may have varieties of those basic instructions in the form of addressing modes. So, we will just go through those names and we will see how much time some of these instructions take, what is the size of these instructions. As I mentioned, the instructions could be 1 word or 2 words or 3 words, and then eventually we will see how we are going to be experimenting with the MSP430 microcontroller in our course by looking at the design of the MSP430 Lunchbox. So, the instructions are they can have double operands here, such that you want to add the values of, as an example, R4 and R5. Here the sum of R4 and R5, which are general purpose registers, is stored in register R5 here. This is the destination. You can have a single operand instruction where you, apart from the instruction, the opcode, you have an operand here. You are saying call a subroutine which is located at an address whose address is located at a flash address whose the address of which is stored in a register R8, and you could have another instruction such as a jump instruction where it is an unconditional jump with the relative, which means compared to your current location you can jump forward or you can jump backward. These are the 7 addressing modes, which means on the basic operation you can, the addressing mode specifies how do you get the operand. And so, we have a register mode in which 2 registers or 1 register is used to specify the operand. You have indexed mode, which means one of the registers is used as an address to go into a memory location to fetch the operand. You have symbolic mode, which is referring to the the labels that you would use in your program, jump here or call that subroutine at that location. You have absolute mode where you are specifying the entire value. You have indirect register mode, which means you are going to use register in an indirect mode. You can do an auto increment on those register values, and you could use an immediate value such as you want to initialize a register with some number. These are 7 addressing modes that operate on the basic instructions and create variety for you. And this is the addressing the source and destination bits that specify each of these modes, as you can see. We are not going to again go into the details of this, because as an embedded system designer we would worry about other issues. Now we have reached a point where we are now ready to jump into experimenting with MSP430 microcontroller, and for that, as you see, as I mentioned here several times, we have designed a microcontroller evaluation kit called MSP430 Lunchbox. Now let me also briefly mention that this is not the only evaluation kit that you have, that Texas Instruments makes several wonderful evaluation kits, and the most popular of them is actually called MSP430 Launchpad. That is their official evaluation kit. This kit is priced very competitively, and if you get your hands on it, you will realize that on this kit there are actually 2 microcontrollers. One of the microcontrollers is the one that you are going to use, which we call as the target microcontroller, and then there is a control microcontroller which controls this target microcontroller and helps you download program into it, or to emulate it, or to debug it. And so it is a extremely competitive and extremely versatile piece of hardware. Unfortunately, it is slightly more expensive than what is possible to make ready with microcontroller by itself, and this is where we come into picture, and we have designed this Lunchbox. As you see, here is our target microcontroller, which is going to be MSP430G2553 in the DIP format. Now I have been mentioning this several times in the past, that there are several ways of programming MSP430 microcontroller. One is through the SPI by wire method, which incidentally is the method that official Texas Instruments MSP430 Launchpad uses. The other method is by accessing the JTAG interface pins, 4 of them, TDI, TDO, TMS and TCK. The third method is using what is called as the in-application programming, what Texas Instruments calls as bootstrap loader, and the advantage of that is you do not need any special mechanism to transfer program from your development host, which is the desktop or laptop computer, into the memory of the microcontroller. All you need is knowledge of which signals to activate and a mechanism to connect the desktop computer and the microcontroller. And today, as you know, one of the most common methods of connecting anything to the desktop computer or laptop computer is through the USB. Unfortunately, the G2553 microcontroller does not have a USB interface. It has a UART interface. So, you have to have a mechanism by which the USB signals from the desktop or laptop computer could be translated and converted into UART, and such a device which converts from one protocol into another has a name, and it is called a bridge. A bridge is simply a mechanism to go from one side of the river to the other side. Likewise, I would say that we need a device which is a USB to UART bridge. Now, there are several mechanisms to achieve this bridge functionality, and we have used an IC called CH340. This is a commonly available bridge integrated circuit. On one side it connects to the USB, and on the other side it has the UART functions, and apart from that it has 2 control signals. One is called request to send and data DTR signal, and these are used to connect to certain pins of the MSP430 G255 series microcontroller in this PI by wire mode only for control. And then because your MSP430 microcontroller operates at 3.3 volts or up to 3.6 volts and not 5 volts, we have taken the 5 volts available on a USB, passed it through this low dropout voltage regulator to provide 3.3 volts supply voltage not only to the microcontroller, the target microcontroller, but also to the bridge. Apart from that, you have a 32.768 kilohertz crystal which is used to generate the bit rate, what is called as baud rate for UART communication. You have a user LED, you have one user switch, you have a reset switch. Other than that, rest of the available pins are accessible through header pins, as we will see in the next slide. Here is the photograph of the MSP430 lunchbox, and let me show you. This is the microcontroller MSP430 G2553. Here is the reset switch, here is the user switch. We have the power on LED here, and a power on LED is very important component to have whether you are designing a evaluation kit or your own instrument, because that is the only way to convey to the user that the power to the system is on. If it was not there and if the system is not working, the user would be confused. Is it not working because the power has not been applied, or whether it is not working because the system is faulty. So, a power on indicator is a good way for that. You also have this crystal which is required, this crystal is required by this CH340 USB to UART bridge. You also have a 32 kilohertz crystal as you saw in the previous slide. This is used by MSP430 for UART communication. The available pins that MSP430 offers you are available on these header pins, and you have a this is the user LED here, this is the user switch that you can that is connected to certain pins of the resident microcontroller, and here are some jumpers you have to engage in certain way as mentioned here. If you want to put the MSP430 kit in programming mode, which means you want to download code, then these jumpers have to be engaged. These are shorting jumpers with which you can connect two neighboring pins. You have to engage them in certain way, and if you want to use the same USB interface for serial communication in your program, through your program during runtime, then you change the setting of these jumpers, and this is mentioned here and here. And this is a transistor which is required for some level inversion. This is the microcontroller that we are using. It has all these features which I have gone through before. This is the schematic. I encourage you to go through the schematic. It has been annotated nicely. Here is the power supply, here is the user peripherals which is switch and LED. Here is the USB to UART bridge, here is your MSP430, and here you have extension headers. This is the layout, and as I have mentioned repeatedly that this layout is available on my blog website, which we have shared, which on the Git website. You can download this and you can print your own printed circuit board and solder all the things yourself, and you can make this evaluation kit yourself. If you do not have it, you can even temporarily put together all the components on a breadboard or a zero board. You can have in-house, you can make your own PCB, or you can get a manufactured PCB from outside. And so, this is the evaluation, the lunchbox fabricated on a breadboard. This is in-house that in my lab we used earlier, and this is the manufactured lunchbox. I hope that you have access to one of these three lunchboxes to be able to continue having extensive hands-on sessions in future. I will see you very soon. Thank you very much.